Okay, sections 5.4 and 5.5 are pretty related, so I'm going to combine those together. The main topic that we're going to talk about is logarithmic functions. Now in section 5.3, we talked about exponential functions. An exponential function is a function of the form y equals a to the x, and an exponential function is always a one-to-one function. Now remember, one-to-one just simply means that the inverse is a function. The inverse is all about switching x and y. Okay, so if I want to calculate the inverse of y equal a to the x, I just simply switch x and y, and I would have x equals a to the y. Okay, now this equation here, this function, is so important that in math that we give it a special name. We call it the logarithmic function. Okay, and here's kind of a more formal definition. It says the logarithmic function to the base a, where a is a positive number. A can't be 1 though. But the logarithmic function to the base a is denoted by the equation y equals log base a of x, is how we read that, and is defined by y equals log base a of x if and only if this equation here, x equals a to the y, happens. All right, a couple things. First of all, this is the definition of a logarithm, and when it comes to the topic of logarithms, I feel like this is the most important thing to know. You have to know the definition of a logarithm. If you don't know the definition, that's going to be a real problem later, because so many calculations that we do with logarithms just simply revolve around knowing this one definition here. Okay, I'll be using this definition a lot. So to me, it's just worth memorizing. Now, in the wording, you'll see I have the phrase if and only if that I'm using. Now, that's a phrase that we see sometimes in various math classes, and what we mean by that is that we have two if-then statements. So one way that you can read this phrase here is beginning to end like you would normally read it. You could say, if y equals log base a of x, then x equals a to the y. Okay, another way to read it and still have it be true is to read it end to beginning. So I could say, if x equal a to the y, then y equal log base a of x. All right, so you see what I'm doing there? I'm going both ways with it. Beginning to end and end to beginning, and both mean the same thing. Okay, so that's what we mean by the phrase if and only if. Now, the logarithmic function is a function, so like any other function, there's input values and output values. X is the input, y is the output, a is the base. Okay, x is not a power of a, so don't be confused by that. You know, when you're using the notation, you really shove the base down there so that it doesn't look like x is a power of a or anything. All right, the base has to be a positive. Okay, can't be 1 though. Now, the domain of any logarithmic function is all positive numbers. All right, you can't take log of 0, you can't take log of a negative. The domain is all positive numbers if you have just a basic logarithm. Now, if we look at an example, okay, suppose that we have this equation here, y equals log base a of x, and I'm going to assign specific values to a, x, and y. The base has to be a positive, I mentioned. So suppose that we have base 2. And suppose that x is 8 and y is 3. Now these are specific numbers that I'm using. And so if I write the equation 3 equals log base 2 of 8, what that means in the exponential form, okay, x is 8, the base is 2, the y value is 3, so 2 cubed would be on the other side. 2 cubed is 8. 2 cubed equals 8, that's a true statement, right? But 2 cubed equals 8, and 3 equals log base 2 of 8, like that means exactly the same thing. It's just how you're writing it. You know, one's using the exponential form, which we're, you know, more familiar with, but the logarithmic form would be representing the same thing. It's just a notational thing. Now, in this example here, I would like us to graph y equals log base 2 of x. In order to graph y equals log base 2 of x, I'm going to have us first regraph y equals 2 to the x, okay? Because y equal 2 to the x is going to play a role in how I get the graph of this logarithm. Now in section 5.3, we have already graphed y equals 2 to the x, okay? And that was in your notes already. Here's section 5.3 notes, and I was just going to show you this table that I've created is the same table that we were using before when we did this in section 5.3. Okay, so I've got that table again, and now I'm graphing y equal 2 to the x. That's an exponential, and the domain of any exponential is all real numbers. So I could let x be anything I want here. Again, I'm just using these same numbers that we had used previously. So like 2 to the negative third is 1 over 2 cubed, or 1/8. Here's negative 3 1/8 on the graph. Sorry, I'm pointing the wrong point. Negative 3 1/8 right there. If x is negative 2, 2 to the negative second would be the same as 1 over 2 squared, or 1/4. Here's negative 2 1/4. If x is negative 1, 2 to the negative first is 1/2. Here's negative 1 1/2. Anything the 0 power is 1. Here's 0 1 on the graph. 2 to the first is 2. Here's 1 2 on the graph. 2 squared is 4. Here's 2 4 on the graph. 2 cubed is 8. Here's 3 8 on the graph. So the curve is rising steadily. After it crosses the y-axis at 0 1, it's going to shoot upward and outward into quadrant 1, passing through these points. One feature of an exponential is that it will always have a horizontal asymptote on the graph. Okay, so while the curve heads outward towards the left, it will never get to the x-axis. Okay, because x is in the power. No matter what x is, positive, negative, 0, doesn't matter. You will never have 0 coming out of the calculation. You'll also never have a negative coming out of the calculation. So at no point will this curve ever get to the x-axis. There's a boundary there. All right, so we have already been there and done that before. We looked at this same graph in section 5.3, y equal 2 to the x, and here's that same graph again. All right, now the first thing that I had mentioned about this topic here is that an exponential function is a one-to-one function. What does that mean? It means that the inverse is a function. Now, inverse is all about switching x and y. So if I want to calculate the inverse of y equal 2 to the x, I just simply switch x and y. And I would have the equation, where we at here, x equal 2 to the y. Okay, now this is an if and only if. So that means that I can read the statement beginning to end or end to beginning. Okay, I could say if x equal 2 to the y, then y equal log base 2 of x. Well, that's the curve I'd like to graph. Okay, so if I want to graph y equals log base 2 of x, I'm going to have to graph the inverse function of y equal 2 to the x. Okay, there I'm saying the word inverse again. Inverse is all about switching x and y. Well, with the points that I've got plotted, let me go ahead and switch the coordinates, the x and y coordinates, and I'll plot those new points. Okay, let me do that now. So negative 3 1/8 is now going to be at 1/8 negative 3. Negative 2 1/4 is now going to be at 1/4 negative 2. Negative 1 1/2 is now going to be at 1/2 negative 1. 0 1 is going to be at 1 0. 2 1 is going to be at, 1 2 is going to be at 2 1. 2 4 is going to be at 4 2. 3 8 is going to be at 8 3. Okay, so I've just switched all the coordinates on this exponential to get this new curve here. Now, the horizontal asymptote that was originally on the graph of the exponential, y equal 2 to the x, is now going to turn into a vertical asymptote on our new graph. Now the new graph represents the graph of x equal 2 to the y, right? The inverse of y equal 2 to the x, but x equal 2 to the y means y equal log base 2 of x. Okay, so this curve would be the graph of y equal log base 2 of x. A couple of things. So first of all, I've got the line y equal x drawn, and I did that on purpose because back when we were talking about inverses, I had mentioned that any function along with its inverse on the same graph are always going to be symmetric to the diagonal line y equal x. That will always happen. Okay, so one way to look at how I got the graph of the logarithm is I started with the graph of the exponential, and I just simply rotated this graph about that diagonal line. All the points are going to land in the same spot here that you see the graph of the logarithm is located. Okay. Y equal log base 2 of x and y equal 2 to the x are inverses of each other. I've got that written on the side here. Okay. Now, the procedure that I'm using here is the procedure that you would use to draw the graph of any logarithm. Okay, you're going to have to start with the corresponding exponential and then flip all the coordinates, just like what we're doing here. So like if I want to graph y equal log base 5 of x, let's say, I would have to first know the graph of y equal 5 to the x, since y equal 5 to the x is the inverse of y equal log base 5 of x. Once I have the graph of y equal 5 to the x, I switch all the coordinates, just like I'm doing here, and I get the graph of y equal log base 5 of x. Okay, now at this point, I want us to make some major connections with things happening in the chapter. I mentioned in a previous video that Chapter 5 is going to seem kind of weird early on here. It might seem like we have no rhythm to what we're doing with the topics. Like, you know, we're doing one topic and then we're going to jump to something else that really has nothing to do with what we just learned, and then we jump to something else that really seems like it really doesn't have anything to do with what we just learned. Well, yeah, these are connected, okay, and there's a purpose. You know, there's a plan for what we're doing, and I hope that you guys see that now. So in Chapter 5, we started with function composition. We also talked about some other operations with functions like add, subtract, multiply, and divide. But function composition was a necessary thing to talk about in order to talk about inverses, right? Because the way to check if two functions are inverses of each other is through function composition. You plug each function into the other, and you check and see that you get plain old x. Well, the topic of inverses is necessary for logarithms because an exponential is the inverse of a logarithm. Okay, obviously exponentials would be a preliminary thing to talk about when it comes to logarithms. So the things that we looked at in sections 5.1 through 5.3, to me those are like preliminary topics that had to be discussed before we look at logarithms. Okay, the topic of logarithms is really just not a topic that you just jump right into until you have that other stuff known. Okay. Now, I mentioned earlier that the definition is super important. We have to have this memorized. I always tell my students, memorize this. You know, if it were in class, make sure that you know that. We're going to be using this definition so many times. Got to know it. So my next couple of examples here are where I'm just kind of having us get some practice converting from logarithmic form to exponential form and then exponential form to logarithmic form. Let's take a look at that now. So here's 3 equations that are in exponential form, and I want us to write them in logarithmic form. Now, when we write the equation in logarithmic form, currently we're in exponential form. We're in the form x equal a to the y. And I need to rewrite that into the logarithmic form, so I need to write it into a form that is y equal log base a of x. Now when I do that, I just simply identify, okay, what's x, what's y, what's a, and then write it into that logarithmic form that you see here. So in this problem, it looks like m is my x value, so that'll be the input into the logarithm. 1.2 is the base, that'd be my a value, and 3 is the power, that's my y value. Okay, so 3 would be all alone on the logarithmic equation here. 3 is equal to log base 1.2 of m. Go ahead and circle, that would be the equation, but now in logarithmic form. Part B, 9 equals e to the t. E, meaning the number e that we talked about in the last section there. What does this look like in logarithmic form? Okay, well, 9 is my x value, so that's going to be the input into the logarithm. E is the base of the exponential, so it's going to be the base of the logarithm. T is the y value, or the power of e, so that's going to be on the other side of the logarithmic equation. T is equal to log base e of 9. That would be the equation, but now rewritten into a logarithmic form. Part C, 5 to the 2x equals 13. Okay, that's an exponential form. I want us to rewrite that into a logarithmic form. 2x is the power, so that'd be my y value. That's going to be on one side of the equation in the logarithmic form. 5 is the base, so it's going to be the base of the logarithm. And 13 is my my input number, I should say. And so that's going to be the number going into the logarithm. 2x equal log base 5 of 13 would be my answer there. Now, I'm not solving for x or solving for m or doing anything like that. I'm just simply rewriting one form into another form using this definition here. Okay. Let's get some practice going the other way. All right, so in this next example, I have several equations that are in logarithmic form, and I want us to rewrite them into an exponential form. Same thing. I just simply identify what is x, what is y, what is a, and I need to write it into this form, x equal a to the y. In the first problem, okay, so it looks like 4 is my y value, a is the base, so a to the y would be a to the 4th here. 24 is my x value, so that'll be on the other side of the exponential. A to the 4th equal 24. That would be my answer. That's the equation, but now rewritten into an exponential form. Okay. The next one, -3 equal log base e of t. What does that look like in an exponential form? Well, t is the input, right? So that's going to be all alone on the exponential there. E is the base, e meaning the number e. So it's going to be the base of the exponential. -3 is the y value, so that's going to be the power of e. T equal e to the -3rd, that'd be my answer there. Now, before we do part C, just one thing that I want you to notice. I mentioned that the domain of a logarithm is all positive numbers. Okay, you can't take log of 0, you can't take log of a negative. That does not mean that you can't have a negative coming out of the calculation. We can have that. That'll actually happen pretty often. Okay, -3 is the y value, not the x value, and of course there's a difference between x and y. Okay, in this graph here, it looks like, okay, here's the graph of this logarithm. By the way, note that the domain of y equal log base 2 of x is all positive numbers, right? I've got a vertical asymptote at x equals 0. That's a feature of a logarithm, by the way. A logarithmic curve will always have a vertical asymptote on it. Okay, that came from converting the horizontal asymptote on the exponential to a vertical asymptote. Okay, so x can't be 0, right? Because I've got a vertical boundary there. X negative. Well, I don't have any graph on the negative end of the x-axis, talking about the logarithmic curve here. Okay, but if x is between 0 and 1, I'll be plotting a point below the x-axis, and so y would be a negative. All right, so be careful about that. You know, you can't have a negative going into the calculation, but you can have a negative coming out of the calculation. That'll happen, you know, here and there. Part C. Okay, log base 3 of x plus 7 equal 5. What does that look like in an exponential form? Well, x plus 7 is my input, so that's going to be all alone on the exponential. 3 is the base. 5 is the y value, so I'm going to have 3 to the 5th on the one side, x plus 7 on the other side. Again, I'm not solving for x or anything like that. I'm just simply rewriting one form over to another form. Okay, and so here'd be my answer, this equation, but now rewritten into an exponential form. And I'm going to go ahead and stop right there.